So now that we've had a chance to talk about what the fork join framework does, we had a chance to talk about the structure and functionality of the fork join framework. I described some of the key methods, both for the fork join pool and for the fork join task. What we're going to do now is we're going to talk about how to apply the fork join pool, and you'll get a chance to see how all the different features we've talked about so far and one of the subclasses of fork join task can be put together in order to be able to implement the solution. The solution we're going to be looking at here is a program that's going to implement operations on big fractions. I'll talk more about what a big fraction is in a second. And we'll use a couple of different fork join pool programming models, so you get a chance to see how they work in different ways. The code that we'll be looking at is all here in the EX22 folder. And so if you're curious and want to know more about how this works, please feel free to take a look at that example. A big fraction is essentially an arbitrary precision fraction class that will be able to have numerators and denominators that are so-called big integers, so they can be arbitrarily large. And there's various operations here to convert numbers into big fractions, convert strings into big fractions, to be able to reduce a big fraction, be able to subtract, add, multiply, divide, compute the GCD, et cetera, of a big fraction. So there's lots of things you can do with big fractions. And this, again, is kind of what the code looks like. When you run the test, it will give you some performance results. And as we'll see, the different approaches we're going to look at will have different consequences in terms of how they work internally. For example, how much they steal, how much they do work stealing, and we'll talk about that. And then also, perhaps even more importantly, how fast they perform. So you see that some of the implementations run faster than the other ones do, and we'll go through and kind of look at some of the different factors that influence the performance of the different implementations of the fork join pool. We're also going to use just a little bit of Java 8 here. We're going to use some functions in order to be able to reduce the complexity of the code, and we're going to use a little bit of Java 8 streams. I'm not going to talk too much about this. I just use it for my test program to make it easier to understand. Here's what the main driver program looks like. It's got a main function. This piece of code here is going to go ahead and generate up to S max fractions. That's just an integer. It's going to generate this many calls to this lambda expression. So make big fraction is a factory method, and that factory method is going to generate a random big fraction. And it's not reduced, so it hasn't been reduced yet. Reduction is simply putting the fraction into its reduced form. So if you have, 44 55ths, then, when you reduce that, you'll end up with 4/5 or whatever that is. So that would be a reduction. So they're going to start out being not reduced randomly with large numbers, big fractions, very large big fractions. And we're going to create up to this many of them, and then we're going to collect all those big fractions into a list of big fractions. And I'll explain more about how this code works when we get further along in the course. So this is just using a generator on a stream to pass this lambda expression. This lambda expression gets called this many times, and then that stream is converted into a list of big fractions. We then have a function which maps big fraction to big fraction. So what this fraction is going to do is it's going to take a big fraction, it's an unreduced big fraction, this thing, and it's going to reduce it, and then it's going to multiply it. So this particular function, as we're defining here, is going to take a big fraction, it's going to reduce it, it's going to multiply it, and then it's going to return the result of multiplying the reduced big fraction by some constant. This is actually a surprisingly large operation. It takes a long time to run this. So if you have very large big fractions, it takes a while to reduce and multiply it. And that's just a burn CPU, right? Nothing more profound than that. And then these are all the various fork join tests. And that's what we're going to spend our time focusing on, how those different fork join tests actually work. So applyAllIter, applyAllSplit, and applyAllSplitIndex are all helper methods. You can see that they take lists of big fractions and some function to perform. We'll take a look at what that is. Over here, we can see this is what the function is. It's the reduce and multiply operation. And these things then call the actual worker methods that do the actual big fraction computations. And what they do is they pass in the list of big fractions, they pass in the operation to apply, and each of these things is going to use a different implementation, apply the fork join pool in a slightly different way, and they're each going to get their own instance of fork join pool. So we're not using the common fork join pool. Each of these test programs gets their own fork join pool, which by default defaults to the number of cores that the JVM knows about. All right, so that's just kind of the big picture view. So you got a list of big fractions, some operation to apply, and a fork join pool upon which to apply the operations on the list. So let's take a look at the first implementation. This is the simplest of the methods. This is one that's called applyAllIter. And so what it's going to do is it's going to apply this this function operation, to all the elements in the list, and it's going to do this iteratively using the fork join pool to run the computations in parallel. All right, and you can find that particular piece of code here in this file. Okay, so let's break this down a little bit. So the first thing we see here is that we have a creation of an anonymous recursive task. So it's a recursive task. We're defining an anonymous instance of a recursive task, and it's got a compute method here that we'll look at in a second. We'll look at its implementation. And this compute method is going to create a bunch of subtasks and execute them in the fork join pool that's passed in here. This code is more verbose than we might want, and the reason for that is, as I mentioned before, fork join pool is not defined as a functional interface, and therefore we can't use lambdas. So we can't replace this use of an anonymous inner class with a lambda expression, even though compute is the one and only abstract method in that class. That's just the way that fork join pool works, and it works that way. Fork join task works that way because it was defined before Java had the concept of functional interfaces. Okay, so once we create this task, it's going to run at the outermost level. It is then passed as the parameter to invoke. And invoke, as you may recall from our discussion last time, is going to go ahead and invoke the task on the fork join pool, and then it's going to wait for and return the results. And the results are going to come back as a list of big fractions that have been reduced and multiplied. All right, so that's kind of the big picture view. Now we're going to zoom in on compute. So this is the compute method. This compute method is what's defined here. And that's the whole thing, and we'll kind of walk through it one at a time. So this is implementing the main fork join task, and then we'll see that this thing splits things up into subtasks. Okay, so this is the thing that's going to be passed as this is the method that will be called on the anonymous object that's passed to the invoke method. Here are a couple of data structures we need internally in order to hold the fork tasks and in order to hold the results of applying the fork join tasks. So you can see we have a list of fork join tasks of type T, where T is the type of the parameter passed to the method, just good old Java generics, nothing complicated there. And then we're going to have, and that's called forks, that's a list of fork join tasks. And then we're going to have a list of results, which is just a list of T's. These are the results of the computations that will contain the reduced, multiplied big fractions. All right, so here's what we do. We're going to iterate through the list, and you can see here that we're using good old Java 7 for each loop, a for each loop. We could do this other ways too, but this is a simple way to do it. So for each item in the list, this is the list of unreduced big fractions that was created by the generate function in the stream. For each unreduced big fraction, we're going to add a new recursive task to our list. So you can see forks is a list. We say forks.add, and we're going to add a new recursive task. This recursive task is also an anonymous inner class. Once again, we can't use lambda expressions, sadly. So what we're going to do is we're going to make ourselves a new recursive task, and this recursive task is going to have a compute method, and this recursive task is going to go ahead and apply the operation. Remember, this is a function. So we're going to apply the function. And remember what the function did, just to reiterate this. Here was the function. The function is going to reduce and multiply the big fraction. So that's what we're going to be doing. So what this is going to do is for each element that is in the original list, we're going to apply that operation to the element on the list. So for each unreduced big fraction, we're going to reduce it and multiply it. And then we're going to return the result of that. And so what we're doing is we're making a new recursive task for each element in the original list. And then after we have created this new task, we're going to fork it. And what fork is going to do, remember what fork does, is fork will go ahead and queue up that recursive task on the calling thread's deck. Remember, we have a double-ended queue. So the calling thread's deck, it's going to go ahead and stick this recursive task on the deck of the calling thread to then be processed when the time is right. So fork returns a fork join task. So we take the result of fork and we add that to the list of fork join tasks. And all of those things have been forked now. So when this list is done, when this loop is done, we will have forked off n fork join tasks, where n is the number of items in the list, and each of those fork join tasks will now be queued, waiting to be processed by the thread or threads running in the worker thread pool, which is what the fork join pool provides. And it'll be the pool in this particular fork join pool. Okay, so we've gone ahead and we've gotten all these things set up and ready to run. I'll show you a visualization of what this looks like in just a minute. But for right now, let's assume that everything is now in queued. This implementation relies on work stealing to disperse these tasks, these recursive tasks or subtasks, to the pool of worker threads that are running in the fork join pool. And I'll visualize that in a minute so you can get a better sense of what it's doing. After all those guys have started to run, or while those guys are running, we then have another loop, and this loop is going to go ahead and iterate through the list of fork join tasks that we just forked. So for each task in the fork join task, and it's going to go ahead and join with each of these things. And remember, when join is called, it will logically block, although not necessarily physically block. It'll actually use this thread to go and do other joins in the background using the model we talked about before, the Jiffy Lube, collaborative Jiffy Lube model. It'll go ahead and get all those various results, which are now results of reducing and multiplying each of the big fractions, and it'll add them to the results list. So we're going to end up with the reduced and multiplied big fractions in this list. And so this will essentially block. There'll be one thread that's kind of joining each of the items. And when everything is said and done, we'll return the list of results that came from the fork join task. This implementation is pretty simple to program. It may not be obvious to understand at the moment because I have to explain a few more things, but I think you'll agree with me that it's pretty straightforward. You make a linked list of the tasks that you want to fork. You make a linked list of the results you want to get from those tasks that are forked, and then you go ahead and go through this thing and basically fork them, and then you go through this thing and you wait for the results using join, and when everything's done, you return the list of results. So that's the basic model. Let's take a look at a visualization, because I think it'll help make it a lot more clear what's actually going on. And actually, I go back and forth on whether I should show the code first, followed by the visualization, or the visualization first, followed by the code. Right now, I'm showing the code first, but I think when you see the visualization, it'll make more sense. So keep in mind, this is the applyAllIter helper method. That's what we just looked at. And when this thing starts to run, the fork join pool we have here has a shared queue. This is the shared queue that's used to take items from non-fork join task clients and get the data into the fork join pool. So when we say fjpool.invoke and we pass in this original anonymous inner class, the invoke method here will go ahead and take this task and it'll stick it into the shared queue. So this is being called from a non-fork join task client. This is just a good old piece of code, right? It's not fork join task client, it's just some other piece of code. It's the applyAllIter context. And what it does is invoke will insert this task into this internal shared queue. And the internal shared queue, of course, is part of the fork join pool framework. So that goes into that pool, into that queue. And then what happens is, as you see, we go through this loop and we fork every element. We create a recursive task and we fork every one of these things. And what that does is that will then, I guess what I should have said was that some worker thread will pull this particular task out of the shared queue, and then it will go ahead and run this particular loop, and it'll stick all of these subtasks, one for every element in the original list, into its own work queue, which is a deck. So it'll just go ahead and do, push, 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 push. So push, 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 push. So that's, or actually take it back. That would be the starting point. This is the top. So it'll be push, 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 push. So it's going to push all the subtasks into the deck for that one worker thread. At this point, you might be saying, what the heck is this good for? Right now, we've just got all the tasks in one thread. That's not going to run in parallel at all. Well, this is where it gets interesting. As the worker thread then begins to process subtasks at the head of its deck. Remember, things always work in LIFO order if you are the owner of the deck. As it's working on the subtasks that are at the front of its deck, of its work queue, other threads in the work pool can come along and steal work from this deck, because those other threads don't have anything to do. Their decks are empty. They're not playing with a full deck, as it were. So in this particular case, they're going to steal the subtasks from the end of worker thread 1's deck, and then they're going to go ahead and process those calls, those subtasks. So this is how the work gets dispersed to run in parallel with the other threads in the pool. And of course, on a multi-core machine, these threads will be mapped to the different cores. Any questions about that so far? So the key point here is that everything gets stuck into worker thread 1's deck initially, because this loop just goes through and says, fork, 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 fork. So they all go into the deck of the calling threads of the calling thread. But then the other threads in the pool will steal the work from the end of the deck, while the main thread, or not the main thread, the worker thread 1 starts to process stuff in its deck. So the thing to remember about this is the overhead of work stealing is high, because these other threads have to go steal this guy's work, and that doesn't come for free. But copying and method call overhead is low. You'll understand in a second what copying and method call overhead means in a minute. The other examples have higher copying and method call overhead, but the copying and method call overhead here is very low. But the work stealing is high. Okay, any questions about that? And then when the join method is called here, and this is the main thread that will be joining. The main thread is doing all the joins. The other threads are just doing the processing. So this thread that does the join can also pitch in to compute subtasks as well. So this isn't actually blocked at all. It's only not going to return until it's able to join something. But what it'll do is that thread can also be used to process work and do computations too. Yeah. So the invoke call is just how we get ourselves into the fork join framework. So that's just notice how we have a fork join pool, we say fork join pool invoke, and we have to give it something to start with. So what we do is we give it an anonymous task, and that anonymous task is stuck into the shared queue. And then what'll happen is that the fork join framework will then start to run, and that will cause one of the worker threads in the fork join framework to execute the compute method. So if we were to go back here, here's the compute method. So remember, this might be easier. So fork join pool invoke, we give it this task. Here's the compute method that corresponds to that compute up here. This compute method will be run in one of the worker threads in the fork join pool, the one that actually probably called it, the worker thread that called this. Or one of the worker threads will go ahead and start to run the compute method. So this piece of code here executes in the context of compute, which is running in a worker thread. And then if we step over here, this code is running that piece of code this is in the compute method. So now we're running in worker thread 1. So one of the threads in the pool is actually running this work. And what it's going to do is it's going to come along and it's going to pull off an item from the shared queue. This guy's going to pull that item off and then start turning it into subtasks. So this piece of code here that doesn't say compute, but that's the context in which it's being run, this method there, that's the part where this starts to run. Yeah, good question. So this is what I was talking about before about the collaborative Jiffy Lube model of processing. Okay, so that's the simple version. That's the straightforward one. And when we look at the performance results a little later, you'll see that it's simple, but it's also not always as efficient as we would like for reasons we'll talk about. Okay, let's take a look at a different way of doing things. So this way is going to recursively split the list using fork join method calls. And this approach here is actually the much more common way of using the fork join pool. The way I just showed you is sort of the easy way to do it, but the problem is you end up with high work stealing. And you'll see in a second how this approach can help with that. Okay, so this approach has a nested class called splitter task. And this extends recursive task, which is going to return a list. And don't be fooled, this is actually returning a sublist, for reasons you'll see in a second. And what this splitter task is going to do, as the name kind of implies, is it's going to partition or split the list recursively, and then it'll take each half of the list and run each half in a fork join task. And then each of those fork join tasks will further split their sublist into sub-sublists and run those in fork join tasks. And then those things will take it and further split it again into sub-sub-sublists, and so on and so forth. And so you'll see how this works. So what we're going to do here is we're going to have fork join pool.invoke new splitter task list. So this is the outermost call to split things, and it's going to start by splitting the entire list. So In this case, it's the whole list that's passed in. And let's say, for sake of argument, there's, I don't know, 100 items in the list or something like that. So new splitter task is going to start with a list of size 100 elements. And it's going to call invoke. And of course, what that will do, as we'll see in a second, is that'll end up calling the compute method on this particular task. Now, let's take a look at what is going on under the hood for our splitter task. So our splitter task is going to have a private field that's going to be used to partition the list recursively and run each half of the list in a separate fork join task. So you'll see how this works in a second. It's really, really cool. So we have a private list called mlist. Splitter task has a private list called mlist. Splitter task is going to go ahead and have a constructor that takes a list, and it'll store a reference to the parameter that's passed into it. We'll see in a second what that parameter is going to be, because it's going to be each time as half the list. Here's the compute method, and I broke this up into two parts because it's actually too long to fit easily into one slide. So remember I told you before that the whole essence of the fork join pool is divide and conquer. And with the divide and conquer algorithm, you typically check to see if you're, done, or you've got only a very small piece left. And if you have a small piece left, you do that sequentially. And if you have a bigger piece, you then split it and then solve each of those parts in parallel. Well, that's exactly what's going on here. So we'll kind of look at the basis case of the recursion first. So here's the compute method. And as we see, as the comment says, this recursively performs the computations in parallel on a subset of the list. So if the list that we have here, this is the list that was passed in to the constructor, if the list at this point is less than or equal to 1, in other words, if it's got 1 item or less, then what we do is we make ourselves a new result list, and we iterate through each element in the list, and there's typically one element. There could be 0 elements, but there's typically one element. But we use a for loop just because that way it scales a little better if we decide to change this to be less than or equal to 2 for whatever reason, or less than or equal to n. So for each element in this sublist, we are going to apply the operation here on that element, and then add the result to the result list. So this is all done sequentially. This is just a sequential loop, and it probably only runs one time in this case, but it's sequential nonetheless. And when we're done, we return the result of the list, which will most likely have 1 element or 0 elements in it. That's the basis case of the recursion. Here's the more interesting part. This is the recursion itself. So what we do is we figure out the midpoint of the list. So let's say the list was 100 elements. So now we're going to have the midpoint, which would be 100 divided by 2, which is 50. So that's where we're going to split the list. And then what we go ahead and do, and we make the left-hand side, the left list of tasks. And what we're going to do is we're going to make a new splitter task that's going to start at the beginning of the list up to the midpoint. And we're going to go ahead and fork off this new splitter task to handle the left-hand side of the list from 0 to mid. So that's a new task, and we've forked it, so it'll be put onto the queue to be run. And then what we do is we go ahead and make a new list for mlist, which is going to be the current list from the midpoint to the end. So now we've got the right-hand side of the list, right? So we've now split the list into 2. And then we tell, in our current thread of control, we say, please do the computation on this new sublist. So this is actually a recursive call. Compute here is a recursive call. It'll call itself recursively. But at this point, we've modified mlist, so it's only the right-hand side of the list. So now we've got 2 lists split in half, both of which now are running in parallel. And then what we do, so basically what this is doing is it's using so-called recursive decomposition to disperse the tasks to worker threads. I'll come back and talk about that in a second. That's really important to understand. And then after compute is done, in the calling thread, we take the left-hand left-hand side of the list, and we join with it. So now we're going to end up joining the results. So after compute is done, we're going to wait for the left-hand side of the list to finish. That'll give us a sublist with the results of the left-hand side. And then we take the left-hand results and we add the results that came back from doing the right-hand side computation. So now we've got a complete list with all the results, and we return that merged list as the result of compute. Obviously, this hopefully is clear, but you need to call compute before you call join, because join is going to block. So compute has to be called first, and then we join with the results for the left-hand side. So we're forking off the left-hand side, we're computing the right-hand side, and then we're joining the results and merging them back together again. So that's classic fork join behavior. Fork a big problem into two smaller problems, then recursively fork the two smaller problems into smaller problems, and then you recursively fork those into even smaller and smaller problems, and then once you've got them down to the smallest size that can be computed, which would be when this test is satisfied, then you go ahead and get the results back and then join everything back together again. So we combine everything and return the joined results. This implementation is harder to program, and it's also harder to understand because it's recursive. So you have to keep track of all the pieces that are being forked and joined and so on. So there's extra work involved. The other thing that's important to note, and we'll talk about this, is that copying overhead and method call overhead is also increased, especially because we have to split things and then join them back together again. So let's take a look at a visualization of this now. This is hopefully going to make it a little bit more clear what's going on and why it's a win. So once again, we start off by saying fork join pool invoke, and we give the new splitter task for the list, and that will go ahead and insert the task into the shared work queue. Now we've moved into the worker thread. So the worker thread is going to pull that thing off the queue. And what we're doing here is something different from before. Remember before, that one thread of control put everything into the one worker thread, put everything into its deck, and then the other threads came along and stole it? Well, in this case, what we're doing is we're partitioning things, and we're forking and computing in different threads. So very quickly, we're going to end up essentially with a balanced tree of subtasks that are more evenly partitioned across the various threads in the fork join pool. So unlike the previous case where we had all this work stealing going on, the way that we're doing this thing recursively will allow the fork join framework to disperse the work to the different threads in the pool more evenly with less work stealing. You'll see specifically when I show you the results how much lower work stealing is happening. So as a consequence, work stealing overhead is a lot lower because we're partitioning it through this recursive decomposition. But the copying and method call overhead is a little higher, because especially the copying, we've got to do all this copying to put things back and merge them back together again. The forked subtasks, this thing here, and the call to compute run in parallel. So this is going to be running most likely in a different thread of control in the thread pool, and this compute call will be running in the calling thread, which will be a different thread from the thread that's going to be doing the fork. This particular way of doing things is very canonical in fork join pool. You typically borrow the parent thread to compute the right-hand side. You don't have to fork off yet another thread. You use the calling thread to do this. It just means there's going to be less forking and joining going on. Okay, join returns a result, and we basically end up with a more balanced tree of join calls because they're running in different threads. Whereas the original version we had, join ran in only one thread, the main thread, or the first thread. All right, so that's variant number 2. I'm now going to show you variant number 3, which is going to illustrate a couple of new things. First, it's going to show how to get around doing all this extra copying. And the way it's going to do that is it's going to put everything into an array that's shared by all the various tasks. So the first thing we're going to do is we're going to avoid a lot of the copying overhead. And the second thing we're going to do is we're going to use a different class called recursive action, which is a fork join task that doesn't return a result. All right, so this is going to be splitting things using an index rather than passing the results back. First thing we have to do, this is really, really weird. So this is how in Java you can make a new instance of a generic array. And do not ask me why it has to be so convoluted. But if you want to learn more about it, take a look at the Stack Overflow link here at the bottom. This is how you make a new array of a certain size, of a certain type that's a generic type. So we have to basically go and say array.newInstance, which is a factory method that will take the class of the element of type T, which is one of the list elements, and we're going to make a new array of type T of this size. And that thing called results is then going to be used by the splitter task that we'll see in a second. So this is a local array in this method that's generic and allocated dynamically to be big enough to hold all the results. And the whole reason to do this is to avoid having to copy the data unnecessarily. Splitter task extends recursive action, and it'll run each half in a fork join task. And then we go ahead and invoke the fork join pool on a splitter task that's going to split the entire list from 0 to the end. So from the beginning location of the list to the end of the list. And it's going to wait for the results. And then what we get back here will be we have an array of results, which is what this thing's going to be putting its results into. And then we're going to convert that array of results into a list and return this as a list of results. Yes, it's somewhat convoluted. Another way to make this a lot simpler is just to change the signature to pass in an array of T. And then you don't have to do all this insanity with this crazy array.newInstance code. Okay. So let's take a look at splitter task that's implemented using recursive action. Remember, recursive action does not return a value from compute. It returns void, which means it's a no-op, essentially. So what we're going to do, since we're not going to store sublists in this implementation, instead we're going to keep track of the beginning and ending index into the list. That's what we're going to use to partition the thing up into pieces. So here's the constructor. We take low and high, and we just stick those into the private fields. And the reason we do this is to avoid the overhead of copying sublists when we merge things back together or we split things up. Here's what compute looks like. This goes ahead and finds the midpoint in the current range, so it adds low to high, and then it divides by 2, which is right shifting by 1. That's just a clever Java idiom. I don't know why people still do that. I'm sure the compiler has long since figured out how to optimize that, but you'll see that a lot in Java code. If mid equals low, then we've got one element, and so we go ahead and apply the operation on the element in the list and stick the results into that results array. So here's the clever thing we're doing. We're simply putting the result directly back in the results array rather than putting it into a sublist that we have to merge together later to make a complete result. So we're just sticking it back in where it goes in the array. Then what we do is so that's what we do if we've got the basis case for the recursion. For the recursive case, we split ourselves into a new left task, which is a splitter task that goes from low to mid, and we fork that. We then go ahead and compute the right-hand side in parallel with the forked left-hand side, and then when we're done, we just call join. And notice how join doesn't return a value because it's a recursive action, not a recursive task. So this simply serves as a synchronization point. It's like a barrier synchronizer that says, wait until the compute is done for the left-hand side that was forked off. And then when it's done, it continues on its way. And this is also known as something called a synchronization point. This will make sure that the memory is properly, the memory that's cached in the different cores is properly pushed out to be correct with respect to the results array. So it's got the right values in the results array. This implementation is also harder to program and understand since it's recursive, and it's also got the kind of wacky results stuff so that we don't have to do the copying overhead. All right, so let's take a look at how this is going to behave. This is going to work very much like the one that's the earlier splitter version that I showed you that used a recursive task. The main difference is this version doesn't have to do the extra copying. So we're going to knock on wood and hope that's going to run a little faster. Once again, invoke sticks the task into the shared queue. And then, as before, we split things up. And because we're splitting them up and forking them in these subtasks, we end up with a nicely balanced tree of calls. The work stealing and copying overhead is low, but the method call overhead is still a little high. It's not really all that bad. We're just doing all these calls to the compute methods that are being done recursively. And the fork subtask and compute can run in parallel. And before, notice how compute is running in the parent. It's not forking another task or subtask to run in parallel with the left-hand side. It's just borrowing the parent's thread to do the compute. Join essentially just serves as a synchronization point. It's not actually getting results back. It's just waiting for the other computations to finish. So we have a nice balanced tree of join calls. All right, so now that you've seen these three different implementations, let's talk about the pros and cons of them. So I think you'll probably agree that the iterative fork join implementation is easy to program, right? You just write a loop. You go ahead and create your tasks. Each task does something. And you fork each task and you add it to your list of forked tasks. So those things all start to run. And then when you're done doing all the forking, you go ahead and join everything together. And when you're finished with that, when that loop terminates, you've got all the results joined together, nice and clean. However, even though this is very simple to understand, it incurs more work stealing. And what I'm doing here is there's actually a call that you can invoke on the fork join pool to say how many steals were used. And so in this particular case, I think I had an array of 32 elements or something like that. So as you can see here, for this version, it work stole 31 times because basically it stuck every element in the original list was stuck into the deck of the first worker thread. And then the other worker threads had to come and steal that work. So there was a lot of stealing going on. You'll see that the other implementations were much lower in terms of their stealing. And as a consequence, because it had more stealing, it also took longer to run. So test applyAllIter took this amount of time to run with a higher steal count, whereas the other versions we'll look at in a second had lower steal count and lower cost. The recursive decomposition implementations, the one that was the two splitter task versions, they had a lot less stealing. And that's because they were recursively partitioning the search space, as it were, so things were getting put into different threads kind of by the way that we designed the recursive decomposition of the tasks. So much lower steal count than the other one. And as a consequence, notice how they ran faster as well. So they're noticeably faster, right? Almost a second faster in one case. However, those implementations are more complicated to program, right? So we had to do all this kind of stuff with keeping track of midpoints and splitting and forking and joining and all this kind of stuff. So the recursive decomposition was more complicated, but it was faster. And if you also take a look, remember we had the two versions. We had test apply all and test apply all split index. Sorry, we have test apply all split and we have test apply all split index. This is the one that used the sublists. This is the one that used the indices and basically put the results directly back into that array, that crazy array I implemented to store the results. Because we're not having copying overhead, the split index one is a little bit faster. Not hugely amount faster, but you can see that reducing the amount of copying sped things up as well. So reducing stealing makes things run faster. Reducing copying also makes things run faster. But these other ones do a little bit more work because you have all these extra method calls to compute because we're recursively doing all the computations. So recursion has some extra work as well. As a general rule of thumb, our recursive action implementation is slightly faster than the recursive task implementation. And that's, again, because we're not having to merge the sublists together. We're taking the results and sticking them directly into the results array. Naturally, your mileage may vary. The other thing is that the recursive action implementation is more idiosyncratic, right? You've got to, if you want to do it the way I did it here, where you use this insane array.newInstance sort of reflective approach of creating a generic array, dynamically sized, blah, 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 blah. That's not the most obvious code to read. Once you understand what it's doing, it's doable, but it's by no means intuitive. Okay, so that's basically, I think, let's see if there's anything left here. Yeah, so generics is the thing that makes this hard. If it wasn't generic, it would be easier. If it was just an array of objects, it would be simpler to deal with. Okay, so that's the end of that extended example.